he's talking on the competition between advections and vortexes.
Thanks, Vladimir. First of all, I would like to thank the organizers for organizing this wonderful workshop and for inviting me. It is my honor to give this talk at IAS. I will talk about the competition between advection and vortex stretching. So here, just a brief recall about the 3D Euler equation. Here, U is the velocity, P is the pressure, and we have the Dalton-free condition. We can take curve on both sides to obtain this vorticity formulation. On the right-hand side, we have the vortex stretching term, and this is the standard advection term. Given the vorticity, we can recover the velocity while this ds of a law. So this part is the local. Whether the 3D Euler is global outpost or can develop by time blow up from smooth data remains an open problem. There are at least two difficulties. The first one is the locality of the velocity, and the second one is the competition between advection and vortex stretching. In this talk, I will focus on the second difficulty. On Monday, Tarek has motivated this difficulty using several 1D models, but let me give one more example. So in 2017, Hao Jinliu introduced this modified 3D symmetric Euler equations. Here, they add this epsilon small parameter in the advection term. In 3D, so here R is the in the cylindrical coordinate, R is the radial component, Z is the Z and theta is the other components in the cylindrical coordinates. And U theta is the angular velocity, omega is the angular vorticity. If epsilon is 1, then this is the exact 3D symmetric Euler. So what they found is for small advection, if epsilon is small, they have obtained strongly more evidence of self-similar singularity. However, if the epsilon is stronger, then similar scenario does not persist. So from this result, we see that the vortex stretching term can lead to the growth of the solution, while this advection can prevent the growth. And there's a competition between these two effects. And in this talk, my goal is to get a better understanding about this competition or cancellation. An important idea obtained by Tarek in Zhang is that one can weaken the advection by choosing some C alpha data with small alpha. And based on this idea, Tarek managed to construct the C alpha singular solution to the 3D Euler. And for this remote solve, so far there's no rigorous proof. And we know that there was a connection between the 3D Euler equation and SQG. SQG is the active scalar equation. Theta is transported by the flow, and U is recovered while this is the local BS of a law. And Constantin-Lax-Majda at the back pointed out that this gradient pull of theta plays a role similar to the vorticity in 3D Euler. In fact, one can derive the equation for this quantity, and it satisfies an equation similar to the vorticity formulation in 3D Euler. So on the right-hand side, this part is, has a similar vortex stretching term. So we expect that there's similar cancellation between this advection term and vortex stretching term. And to study this SQG, we can focus on one specific scenario, this so-called hyperbolic flow scenario. On Tuesday, Yao already introduced this hyperbolic flow scenario, but let me just recall it. The solution theta to the SQG satisfies some symmetry. It is odd in X and Y. It is positive in this first quadrant. Due to this sign information induced this clockwise flow in the first quadrant. And now since we have this symmetry in both directions, we have this hyperbolic flow structure in R2, at least near this point. And these properties are preserved by the equation. So now we can derive the equation of theta sub x from the SQG equation by simply taking the derivative. So if one try to study a growth of the SQG, one driving force is the right-hand side, this term, because this term has strong alignment with this part. So this nonlinear term also contains theta sub x. And in this hyperbolic flow scenario, we see that due to the compression in the x direction, so we have this compression, the x derivative of the horizontal velocity is negative. So because the flow is go to this direction, so it is negative. Therefore, this coefficient is positive, at least near this origin. So this nonlinear term has a right sign to generate a growth of theta sub x. Now note that we have this incompressible condition. So we can derive minus u sub x as v sub y. We can use this incompressible condition to derive the last inequality. Now the point is for smooth data, we can do a Taylor expansion around this line. We focus on this part, this turn and this turn. And for smooth data, we can do a Taylor expansion around this axis. And then we can show that the main turn in this advection turn and the main turn in this vortex junction turn, they are balanced. So we see that there's some cancellation between this advection and vortex junction, at least near this axis. And we see that the cancellation is due to this incompressible condition. So this is the first lesson we learned from this simple calculation. And Castro and Cordova observed that the SQG has this special class of solution. So if theta is a solution to the SQG, then G, this function f satisfies singular model. This is called the Gregorio model. Under this connection, the blue turns, these two turns are exactly zero. And these two red turns reduce exactly to this advection and the vortex junction. Moreover, this B sub law reduced to this B sub law, and H is a Hilbert transform. And this hyperbolic flow structure reduced to this this picture, but let me draw explain a little bit. So the solution in this model will be odd function. Now here, suppose this is the origin in 1D. The solution will be an odd function, and it will be negative in half of the domain. So this is, I will call this function omega, but here is not, here is f, but I draw it here as omega. And the flow is moved away from the origin. So I will use this configuration many times in this talk. So this configuration actually relates to the hyperbolic flow in the SQG. So now we see that there's some connection among the vorticity in 3D Euler, gradient theta in SQG, and the solution to this the Gregorio model. So our goal is to try to use this model to understand better the cancellation in the SQG and the cancellation in 3D Euler. And in the literature, there are other 1D models for the advection and vortex stretching. For example, this generalized Constantin-Lax-Majda model. If A is 0, this is the Constantin-Lax-Majda model. If A is 1, then this is the Gregorio model. Algindia and John observed that for this model, if A is bigger than 1, then this model is related to the generalized SQG via this connection. So suppose that theta is a solution to generalized SQG, then this function G will solve this equation up to some lower order term. So this class of models actually has some connection to the generalized SQG. And for this class of model, singularity formation has been well understood for this range of parameters. So A is less than 0. And it has been studied by Constantin-Lax-Majda, Cordova, Fonteras, and Castro. The specialty of this range of parameters is that for negative A, there's no competition between this part and this part. So we are in this talk, I will focus on the positive parameter A bigger than 0. Then there will be cancellation between these two effects. So there's several conjectures for this class of models. The first one, I will write it down here. The first one is for the Gregorio model, which is the case A equal to 1. The Gregorio model exists globally from smooth data. So this is we have global for smooth initial data. The second and third conjectures are that this model can blow up in finite time for A less than 1 with smooth data, or when A equal to 1 with C alpha data. So this is conjecture 2, A less than 1. For A equal to 1 with C alpha data. This is conjecture 3. And the borderline case in this conjecture is A equal to 1 with C1 data. The specialty of this class of data is that formally the advection and vortex junction turn, these two turns are balanced. To understand this, we can do a Taylor expansion around the origin. Now for C1 data, the vorticity is linear, the velocity is also linear. So once we do this Taylor expansion, we see that these two turns, the advection and vortex junction turn, these two turns are balanced. So at this borderline case, since they are canceled, when we expect that the solution exists globally. That's the meaning of the first conjecture. The second and third conjectures are below this borderline case. The advection turn, when we expect that the advection turn is slightly weaker than the vortex junction. Since this cancellation is not exact, then when we expect finite time blow up. So this is meaning of second and third conjecture, at least from heuristic point of view. However, to justify this heuristic is difficult because this model is non-local. We have this single operator Hilbert transform. The first result of singularity formation is obtained by Algindi and John. They prove finite-time blow-up of this model from smooth data for small a, or from C alpha data with small a alpha. So A can be arbitrarily large, but they need to sacrifice regularity by training a very small alpha. In both cases, the advection term is treated as perturbation to this vortex stretching term, thanks to these small parameters. And the stability of this blow-up is later further studied by Algindi, Go, and Masmodi. The first result toward the global regularity or first conjecture is obtained by Jiajie, Stewart, and Schwarz, where they established the linear stability of this steady state using spectral theory. As a result, this model, the first conjecture, the Gregorio model is global for initial data around this steady state. And I first learned this nice problem from Vladimir a few years ago. And later, Euler established that for this model, it is global for the Gregorio model. It is global for initial data with positive or negative vorticity. The specialty of this class of data is that the vortex stretching term is harmless in the sense that if we remove this advection term and only focus on the effect of this vortex stretching term, the resulting model is global for this class of data. So this part does not generate fast flow of the solution. And the recent trial with Tom Howell and De Huang, we proved that this Gregorio model can blow up on the real line from smooth initial data with compressible. So this result, on the real line case, this result disproved the first conjecture. It also resolved the third conjecture because now the data can be C infinity rather than C alpha. And it can also be seen as the endpoint case of this second conjecture because the result is A equal to 1. Here, the solution when consider, this solution is odd, this is origin, and the solution is odd and negative in half of the domain. So this picture is the same as this configuration. Initially, the solutions look like this, and then grow like this, and then grow like this, and grow, and further grow. So it has some asymptotically expanding nature. And we can write down a solution, the expanding self-singularity in this form. The vorticity will blow up at the spatial infinity. Now, why we have this blow up at spatial infinity? The mechanism is that in any finite x, finite domain, the advection term, vortex stretching term, these two terms exactly cancel. Therefore, the solution remains finite for any finite x. But if you focus on along the trajectory, since this flow is moved away from origin, the flow goes to this direction and goes to this direction. Along the trajectory, due to the vortex stretching, so the solution can still has fast flow. And then it blows up at spatial infinity. And in fact, similar expanding singularity has also been observed for this model on the real line by the work of Rozhenikov and other people. So the range can generalize for all of patterns A. So this, we already get quite a good understanding about the blow of this problem on the real line, at least in this bottom line case.
It goes past 1, right? For the numerical result, right?
No, cannot pass 1. They do some simulation for A bigger than 1, but they do not make some, it's not conclusive.
Ah, it's not conclusive.
Yeah. So for A bigger than 1, it's not know what happens there.
So what do they have for A greater than 1? What do they show?
They show the solution may not blow up, but yeah, that's
Okay.
what they show there. Thank you.
Excuse me, and data can be compactly supported.
Compressible C infinity. You mean this one?
Yes.
The result we can show is C infinity. So it's very nice initial data. But however, the solution at the block time is not finite nature because it has expanding nature. Okay, so in the rest of the talk, I will focus on the circle case or the periodic case with pi period. So next for this problem, we recently we showed that for this model, if A is slightly less than 1, we can construct a block solution with smooth data. And for A equal to 1, we can construct block solution with initial data that's only C alpha at 1 point and smooth elsewhere. And this regularity alpha can be pushed to arbitrarily less than 1. So the first remark is that this result, the theory 1, actually resolves this second conjecture, the endpoint case of the second conjecture, because now we can push to arbitrarily less than 1. And the second conjecture also resolves this the first conjecture, because for n to 1, we can also push to any alpha. And the meaning of these two results is that below the borderline case a little bit, where the direction is formally weaker than the vortex section, we can indeed prove that the vortex section dominates and we can get blowup. The behavioral solution is similar to this Ricardi type ODE, so I will use this to illustrate why we have this blowup. The vortex section turn formally has size 1, and this advection turn has size beta. In both results, in the first result, beta is given by this parameter A, and the second result, beta is given by this alpha. So you see why we require this, why we have this requirement that less than 1 and less than 1. If we require these two parameters to be less than 1, then this parameter is positive, 1 minus beta is positive, then this Ricardi ODE can blow up. And the block term in these two results is T is given by C over 1 minus beta. As beta goes to 1, the block term goes to infinity. So we see that the vortex section then try very hard to get a blow up. And we also see that the advection has some effect that try to prevent the blow up. And let me give some brief idea about the proof. So this result is inspired by the numerics of Loshnikov et al. They discovered that for this model on the real or circle, it said that you have this kind of cell-similar behavior. However, they cannot push to A equal to 1. So when A close to 1, they cannot do the numerics. So they only the computation is only limited to this range. But in my case, I'll focus on A is close to 1. So recall that for A equal to 1, this model has a steady state. This steady state model for this steady state is linear stable. Our idea is to try to perturb this steady state in a non-trivial way to get a blob solution. So this idea will be quite surprising because if one try to perturb something stable, they will still expect to get something stable. But here we'll get a blob result, blob solution. We decompose the solution into the amplitude, this C, and the profile. And the main part of the profile is given by this steady state. And this part is a perturbation. The amplitude C satisfies this ODE. The coefficient is given by 1 minus A plus this perturbation. And the key point to show that this perturbation is low order of order 1 minus A squared. So here we focus on A very close to 1. And this part is 1 minus A, the main part is very small, but it is the main part. And the last order is 1 minus A squared. So as long as A is arbitrarily close to 1, then this coefficient is positive and remain positive for all time. So then we can prove that C blows up. This implies that the solution blows up. And for A equal to 1 with C alpha data to prove the first conjecture, the idea is similar, except that we perturb this profile to get a C alpha profile. The reason we need to choose C alpha profile is that we need to weaken the direction by choosing C alpha data. This idea is originally in Algini and John's work, where they need to choose alpha to be arbitrarily small. But here, alpha we can push to alpha arbitrarily less than 1. And to prove that this perturbation, omega and epsilon remain small, we need to use this linear stable result implicitly. So the actual proof is use a slightly more complicated language that is based on a dynamic scaling formulation and our previous method. So this is the part. This is the story of the blow up of this model. So before I move to the opposite side, any question? So okay. So just I showed that for this model, the blob can occur for this model with positive parameter. This blob results all developed from this class of initial data with this sign properties and this symmetry. So now the question is, what happened at the borderline case? The borderline case means the first conjecture with C1 data and this Gregorio model. Now, however, to prove this result, the difficulty is this model cannot be solved explicitly, and we don't know any a-priori conserved quantity for this model, a-priori coercive conserved quantity. So in general, we don't know any. And from our previous C alpha broad result, any ALP norms of this model can actually blow up. So they are not conserved a priori or a priori bounded. Due to this difficulty, the only known result, the existing result, is the global existence for initial data around this steady state. So the only existing result is a perturbative result. Our goal is to try to show that we can say more than this. And to study this problem, we first established the follow-up criteria. We consider the H1 initial data in this class with this mild assumption. This assumption will be true for generic data. For example, for smooth initial data with finite degeneracy, this criteria satisfy automatically. We show that the solution to this model blows up if and only if this quantity blows up. We know that for this model, we also have the BKM type block criteria that the L infinity norm of the vorticity or the Lifshitz norm of the velocity controls the blow up. Here, we replace this L infinity norm by this one point. The meaning of this criteria is that under this sign and symmetry properties, the gradient of the velocity blows up, most likely to blow up at the origin. So that's why this point can control the blow. And in our previous CLR block results, we can actually choose the initial data in this class. Therefore, this criteria can be actually achieved. So this criteria is shown. And this criteria actually has some connection with other equations. For example, here I recall the Constantin-Lax-Majda model given by this. This model removes this Advection term. And this model is well known that it can be solved explicitly. Using the exact formula, one can show that this model satisfies the same block criteria for this class of initial data. But however, for this model, we cannot solve it explicitly, so it is not clear why holds true. And actually, the similar criteria also hold true for singular solution constructed for 3D order and 2D Boussonec, in the sense that the gradient of the velocity at the origin also control the blow up for the singular solution. But however, for more general solution to 3D order and 2D Boussonec, we don't know similar criteria. And based on this criteria, we show that for initial data, for C1 initial data in this class, and with this mild assumption, this the solution to this model does exist globally. So in this class, in this class, we show that for C alpha data, it can blow up, but now for C1 initial data, it exists globally. So combining these two results, we see that the blob results and the regularity result are indeed sharp. And as we also will, in the proof, we will see that as the vanishing order of the solution increases near the origin, the effect of the direction increases. And in the C1 case, the direction is strong enough to prevent the blow up. To understand why we have these two types of different phenomena, we can do this simple calculation, this formal derivation at the origin. The ratio between the advection and vortex structure is given by alpha, which alpha is the vanishing order of the vorticity near zero. So if alpha less than 1, then this advection is weaker than the vortex structure, blobs can occur. If alpha is bigger than 1, then vortex structure is slightly bigger than the direction is slightly bigger than the vortex structure. So we get then here we show that the solution exists globally. But this is only some formal derivation, and these two results justify this heuristic. And now recall that on the blue line, I first showed that this model can blow up from smooth initial data in this class. But now on a circle, we show that this model can actually exist globally from smooth initial data in this class. So we need to understand why they have different behaviors. This can be understood by studying the L1 evolution. Now, firstly, on the blue line case and the chaotic case, the Hilbert transform are different. So one is given by this 1 of x, one is given by the cotangent x. And the evolution of the L1 norm is governed by this interaction. Now the specialty of this class of data is that omega x and omega y have the same sign in half of the domain. So in this interaction, this pi is always positive. Now on the real line case, this kernel is also positive. So it can generate infinite growth because this integral is always positive. The interaction is positive, so it generates the growth. However, on a circle, we have the cotangent kernel. It has different sign. It can change sign. Near zero, this cotangent kernel is positive. Then near pi over 2, this kernel is negative. So in this interaction, part of the interaction is positive, another part is negative. So the negative part can potentially prevent the blowup. So there's one of very important difference between this model on the real line and on a circle. Now, the specialty of the gradient of velocity at the origin is that this interaction can be controlled by this quantity. So the use of x0 times the L1 norm control the interaction. Therefore, using a simple ground-wall inequality, one can control the L1 evolution using this quantity. But however, for control for free order of this model, in order to control the blowup, we need L infinite of the vorticity. Here, L1 norm is still much weaker than L infinite norm. Okay, so here's the outline proof. In the rest of the talk, I will focus on the proof of this result. So firstly, on the circle, we show that there are two special points. One point is 0, another point is pi over 2. So recall that here I focus on pi period. The solution is pi periods. So you can think about this point 0, this pi is pi over 2. They're the same, and minus pi over 2. These 2 points are a special point in the dynamics of this model under this class of initial data. And we need to perform energy estimate near these 2 points separately. The second step is to quantify that the advection is stronger than the vortex stretching. This is done by studying a quadratic form. The most difficult step is to control this 1 point. And there are 2 cases. In the first case, we can find a new monotone quantity. And in the second case, is the most challenging case, and we do not have this monotone quantity. In the proof, we need to use some specific and hidden structures of this model. But since this model is can be derived exactly from SQG, so some structure might be useful for SQG. And I hope the argument will be interesting for the audience. So the first very special structure of this model is derived by Ren. They derived this equation from this Gregorio model. Now, on the right-hand side, the first term is in conservation form. The second term is a quadratic form. Yeah.
It's like this conservation law. Is there anything like it in SQG?
Yeah, but you need to assume something. Yeah, for example, maybe you can. So first, there's no, I think. But if you consider perturbation of the assumption, you can write it down, start with some lower term. And they consider positive vorticity. So therefore, this quantity is well defined. And this solution, this equation preserves this property. So if for positive initial data, it remains positive. This can be done by a maximal principle. They perform energy estimate on this quantity. Then the first integration of the first term is 0, just by integration by part. The integration of the second term is also 0, using the anti-symmetric property of the Hilbert transform. So here there's some special properties of the Hilbert transform, and this term will be 0. This implies that this energy is conserved, and this energy is the H1 weighted is the H1 norm of the square root of the omega. Using beta implies that the vorticity remaining L infinity. Now, once you have the L infinity control of the vorticity, then you can apply BKM criteria to control the blowup. That's why they can obtain this global regularity. Although in our case, the solution is odd and change signs, and here's 2, 0, at least 2, 0. So we cannot apply this argument. The first thing we try to do is, instead of estimate that quantity, we choose a function g in this class, an odd function g with these sign properties, so that the integral is positive pointwise. And since g is odd function, omega 0 at the origin, so it induces a singularity in this quantity. But G can cancel this quantity. So now this quantity is pointwise positive and is well defined. So we can perform this. We think this is a good energy. But G we need to choose to be determined. Now on the first term, we still have this conservation form. In the second term, we have this quadratic form. The starting point, we'll choose special G so that the second term is 0. This is inspired by our previous work on this model on the real line. We found that for the Hilbert transform, we have many lines non-local cancellation. For example, we have these identities on the real line. On a circle, we also have similar cancellation. So here we just choose sine 2x. This pi is 0, not because this integrand is odd function, it is an even function. And this pi is 0 because we use the special properties of Hilbert transform. Next, for the first term, we can perform integration by part to move the derivative x to g. Then we derive this quantity. The black term is the energy we are trying to estimate. This pi is our energy. And the red term is the coefficient of the linear term. It's given by u times cosine 2x over sine 2x. So let's stare about this term. What's the special about this term? It is quite special because usually when we perform energy estimate, for example, for 3D order or Fourier equations, we usually get a quantity. The coefficient of the linear term is given by is of the order gradient of the velocity. For example, one can perform energy estimate about this model, the L2 estimate. This quantity is given by the gradient of u. But here, this red term is quite special because it is of lower order than this quantity, except at some point. For example, if this pi is 0, then they are forming the same order. But away from the singularity of this sine 2x, this quantity is smoother than the gradient of u. So we use the structure of this problem in a two essential way. One way is to derive the cancellation for the second part. Another way is to perform integration by part to move the derivative to this explicit function g. So for this model, this is very special structure. Now we still need to estimate the second term. Using the property, the side property, we can show that the velocity u is positive. Vorticity also has a special sign in half of the domain. Therefore, we can decompose this integral into two parts. One part has a good sign, so that we do not need to estimate it. Another part is a bad term, but it is supported near 0. So in the bad term, this coefficient is comparable to u divided by sine 2x. So we need to estimate this bad term. Using the formula of the velocity, we can write it in this way. So just use the formula of the Hilbert transform. But the specialty is that this is roughly the L1 quantity of the vorticity. Up to some log singularity, this is very weak singularity. Therefore, we can put this integral away from log singularity, we can put it into L1. Near the log singularity, we can put it into L infinity. So this is a stand-up type extrapolation argument. We can control this u divided by sine x using this estimate. So this is an extrapolation estimate, and it is crucial for this problem. Now, recall that our energy is A omega. This quantity is roughly the H1 quantity of omega. So we will expect that this quantity can invade to L infinity of the vorticity because this is 1D. This is done by using this interpolation. So here, omega is in the denominator, and this part is in the numerator, so they cancel out. Therefore, we can use this interpolation to control the vorticity near 0. Okay, now using all of this estimate, we derive these very crucial inequalities. So when we obtain these inequalities, the first thing one can see that if this part, the black terms are constant or bounded, then this estimate shows you that the energy A can grow at most double exponentially fast. So that's why we can control the energy A for all time. Now, recall that the specialty of this quantity is it can control the evolution of the L1 norm. It can also control the evolution of this point. So using this quantity and Ground's law, we can control this point and this point, so this point can be seen as bounded. And then by solving this inequality, we can obtain the control of this energy A omega. Therefore, we can control this energy E, and by interpolation, we can control the vorticity near zero. But however, we cannot control the vorticity away from zero because this way is zero at pi over 2. So we still need to do something. This is done by controlling another special quantity, this quantity, and by starting in quadratic form and using this energy E, which we have estimated. But because this is quite technical and due to time constraint, I will not discuss this part. But now, once we have the control of the vorticity near zero and near pi over 2, so these two special points, we will control the vorticity. So by Majda Bloch criteria, we can control the solution for all time, as long as this part is bounded. So this is the proof of this one-point Bloch criteria. It used quite a lot of special structure of this model so that we can use this only one point to control the evolution. This is possible because this model has very special structure. The most difficult part is to try to control this quantity. This one natural approach is to try to derive the ODE of this quantity. Because this quantity is positive, the right side, this quadratic linearity is a bad term. It is a very bad term. It suggests that this quantity can actually blow up. For example, if one remove this term, then this is naive. ODE shows that this quantity blows up. And in fact, in our CFR blow result, this quantity does blow up. So due to this difficulty, this evolution inequality is not a good equation to estimate this quantity. Alternatively, we observe that this quantity can be written as the weighted L1 norm of the vorticity. So this actually motivates us to estimate another quantity, which replaces 1 by beta. So instead of estimate this integral, we estimate more singular one. Beta is bigger than 1, so this part is more singular. We want to show that if this Q is bounded, then you can further use this quantity to control this point. So this quantity is actually motivated by our previous work on this to estimate this quantity. And in fact, most derivation on the circle I will show is actually inspired by the case on the Euler. Therefore, to simplify the presentation and to simplify the kernels, I'll focus on the Euler to illustrate the ideas. So on the Euler, the Hilbert transform is given by this, which we are very familiar with. The evolution of this quantity Q is governed by this quadratic form. This is done by just integrate both sides, then obtain this evolution. Now we can use the formula of the velocity, and using integration by part and symmetrizing the kernel, we can show that this quadratic form is governed by this kernel P beta. And the log term in this kernel comes from this advection term. And another term has the opposite sign. So this part has is positive. This part comes from the vortex structure term and it has the opposite sign. So at this point, we see that this quantity actually captures the competition between the advection and vortex structure. This two parts has opposite sign. Our goal is to show that this quadratic form is positive. This will allow us to show that this kernel Q is monotone decreasing. Once we have this kernel Q is monotone decreasing, then we obtain this important a-priori estimate. And also the positivity of this kernel B will implies that the vortex structure term, this advection term is somehow stronger than the vortex structure term. So this will be our second step to quantify the effect of advection and vortex structure. So here I just copy the formula, copy it here. Recall that this solution omega is negative in half of the domain. So omega x times omega y is positive. So to show that this quantity is positive, one natural thing one can do is to show that this kernel is positive. So if the kernel is positive, then this interaction is positive. Now we can derive the asymptotic of this function. This function I call it S function. We can derive the asymptotic as S goes to infinity. The asymptotic is governed by beta minus 2 times S beta. So to obtain the positivity of the kernel, we need beta at least 2. And moreover, for larger beta, it is more likely that this kernel to be positive. Now, so suppose that our vorticity is vanished to y to the a power. In order for this, our function q beta to be well defined, and this duration to be well defined, we require that beta is less than a plus 1. Otherwise, this one is not well defined. So from this calculation, we see that the borderline case for positivity, at least from this heuristic argument, beta should be at least 2. And if beta is 2, then this a should be 1. A equal to 1 means that omega vanishes at least linearly. And this linear vanishing order corresponds to the C1 case. So this corresponds to this borderline case. So we actually, from this formal derivation, we relate this positivity of the kernel and this borderline case. However, this argument can work if beta is large, for example, 2.2. But at the borderline case, this argument fails because this kernel is not positive for some point for some s. For some s bigger than 2, it is not positive. However, using our alternate approach, we can indeed show that this quadratic form B2 is positive. But we need to something. We need to assume that the solution vanishes at the origin, the slope vanishes at the origin. So the vorticity vanishes to y plus 1 plus epsilon power. This is crucial, otherwise this one is not well defined and our energy is not well defined. But this does give us something. It shows that the direction is stronger than the vortex structure if the solution is vanished more than linearly. So strictly more than linear. The proof of this estimate is quite interesting. It is based on the idea of Spoker's theory for a positive defining function. This finish states that for quadratic interaction with this convolution kernel, it is positive if only if the Fourier transform of the kernel is positive. But however, we cannot apply this argument directly because our kernel is not a convolution kernel. But our observation is that we can perform a transform to reformulate this kernel to get a convolution kernel. So we can find a nice transform to reformulate this part, get this part. The key step is to reformulate this kernel P beta theta. Our observation is that we can introduce two parameters B, C, then y divided by x can be written as the exponential of C minus B. So the ratio now becomes the exponential of the difference. And this kernel P beta theta becomes some function of the difference. This is the key step why we can reformulate this part to this part. And then by checking this condition, we can show that this quadratic form is indeed positive. But somewhat surprising fact is that this argument can be generalized to a case on a circle. So in this derivation, we use some homogeneous properties of this function S or this singular function. And the real line scaling is dilation invariant, but the circle is not. So it is a priori it's not clear why this can be generalized to the circle. This is one surprising thing for this problem. Now, based on this estimate, this quadratic form is negative. We have the monotone decreasing of this function Q. So now this function Q is a priori bounded. Because it's a priori bounded, we can use this one to control the L1 evolution. This argument is similar to the one I mentioned that the gradient of velocity at the origin control the L1 evolution. It's for the same reason. Now, using the Holder's inequality, we can further control this one point by interpolating Q beta and L1 naught. So thanks to our one-point block criteria, now we can obtain global existence. So this is the argument in this with this assumption, this vanishing condition. The most difficult case is to try to remove this condition. The problem is if you remove this condition, this integrand is roughly given by 1 over y. So 1 over y, you have a log singularity that's not integrable. Then this argument fails. But now, how about we, instead of consider Q2, how about consider Q beta with beta less than 2? Just now we see that if beta is 2, we get a 1 over y singularity. But if beta is less than 2, the kernel is less singular, then this part will be well defined. It is integrable. So 2 is just a threshold, but if you move across a little bit, then we can define this Q beta. But now the problem is, as I mentioned earlier, if beta is less than 2, we do not expect that this quadratic form to be positive. However, we can in fact quantify that the gap away from positivity. It is of order 2 minus beta. So B beta is not positive, but it's bounded from below by some very small quantity. As beta goes to 2, then B beta will be positive, almost positive. So this quantifies that the advection is almost stronger than the vortex stretching if the advection one is at least linear. So this case applies to our borderline case. Okay, now with this defined estimate, we can obtain a new estimate for this energy Q beta. But if we first start it at this estimate and neglect this remainder term, what we can see immediately that this quantity U sub x0 controls Q beta. So this function can be controlled by U sub x0. However, this is not the thing we want because we already showed that this point controls everything. It controls the blowup. Now the only hope is to try to use this small parameter 2 minus beta. If we take beta goes to 2, then we expect that this linear term is not too bad, thanks to this small factor. But in order to do so, we need to first close our energy estimate. The difficulty is that this quantity Q beta cannot control U sub x0. So this linear term cannot be controlled by our NHQ because this the integrand is weaker than this integrand here. Therefore, away near power 2, we cannot control this quantity. For the same reason, we can rewrite this interaction as this quadratic form. And using our NHQ, we can only control this interaction near 0. Away from 0 and near power 2, we cannot control this form. So then we don't know how to do that. And for a very long time, I believe that this is not doable because we do not have a power estimate. We do not have other things. So how can we control this part away from 0? But so far, I have not told you that why this the domain is a circle plays a role. So why they have difference between the real line and circle? The difference is again captured by this evolution L1 norm, which I have discussed earlier. The L1 evolution is governed by this interaction. The interaction is positive near 0, which is a bad term. Away from 0, this is a good term because the kernel change sign. On the real line case, we only have the bad term, the first bad term. But now the special thing on the circle is that we obtain this negative term, this damping term. I call it this magic damping term because this term is somehow hidden in this evolution. And you can only see this term by comparing the case on the real line and on the circle. Now, since this damping term is supported near power 2, we can use this damping term to control the interaction in this forcing term away from 0 and use our NHQ to control interaction near 0. Therefore, now we can control this linear term by Q square and this magic damping term. For this first bad term I, it is supported near 0. Therefore, we can use our NHQ, which is more singular near 0. So Q can control this bad term, the first bad term. Now, combining these two estimates, we see that we can control the energy estimate now by just combining these two parts. But the key point is, in the first inequality, we have this small parameter 2 minus beta. But in the second estimate, we do not have small parameter. So the second estimate itself is not a good estimate. Therefore, we only add some very small part, 2 minus beta is very small, to our energy to close our energy estimate. If we add a large part, for example, bigger than of order 2 minus beta, then it will lead to a much larger constant and we will fail. Now, we derive this energy estimate for this closed energy estimate. But we need to use one more thing about evolution. The slope of the solution is conserved. This is the derivative of the solution. This part is conserved by the equation. Using this conservation law, for Q beta, we can derive something. Because the slope is given by A, so this integral is roughly A times y to the 1 minus beta power. So the main term of this this Q beta, this functional, is given by A over 2 minus beta. Here up to some low order term. The low order term can depends on the norm of C1, can depends on C1 alpha norm, but it is low order in terms of 2 minus beta. Now, using combining all of this estimate, we can close the estimate for the energy H. It satisfies this estimate, and also with this asymptotics. Usually, if you have the linear term, we can only say that control the energy for a short term. But now the specialty of all of these estimates that thanks to this small parameter 2 minus beta and this asymptotic, using a simple but actually very surprising calculation, we can find that there's a fixed time stack tau in the increasing sequence beta n, this then increasing, but still less than 2. Such that for any n and beta n, we'll control this energy h beta n for this time period with fixed time with length tau. So each beta n will control it for a fixed time, but now the time step is fixed, so we can control it here and one time period, the second time period, another one, and therefore we can control this energy for all time. And it's somewhat surprising that this beta n does not hit 2 in finite time. So that we can control this energy for all time. But the surprising thing behind this should not be surprising, because if one takes the limit beta goes to 2, then we'll see that this linear term is essentially linear if we take beta goes to 2. So we expect that this energy, instead of governed by some quadratic evolution, is essentially governed by some linear forcing term. So the energy can grow exponentially fast. That's why we can control this energy for all time. So if it grows exponentially fast, then it is bounded. Now, thanks to our using this energy H, and again using the Holder's inequality, we can use these two special quantities to control the 1 point, E sub x 0. Then thanks to our 1 point block criteria, we can obtain global existence. So this is a story of this global existence. It is the mechanism behind the proof is that due to these special sign symmetry properties, the solution is most likely to blow up at the gradient of velocity is most likely to blow up at the origin. And the mechanism of the direction is to try to prevent the blow up of some weighted L1 mod. So I think this is one important lesson through this derivation, that the mechanism of the direction is to try to prevent the blow up of some L1 mod. But for the Euler, we know that the R&V norm of the vorticity controls the blow up. But if we have some special blow-up criteria, for example, blow-up criteria like this, and we know that the direction can prevent the blow-up of some weighted L1 norm, then maybe this provides some insight to prove to control the blow-up of other equations, similar equations. Another thing will show that the mechanism of this blow-up is come from incompressible condition. And another lesson we learned from this calculation is that for free order equations or SQG, this problem, the blow-up of this problem from smooth data still remains open. But I think one thing to do is to understand new mechanism to weaken the direction. On Monday, Charles talked about some new ideas for CFR data, and it will be very interesting to see if that ideas can apply to a smooth case. And thanks for your attention.
Any questions?
Actually, I have two. So first one is comparing torus and real line.
Yeah.
You are saying that on the real line, the blow up is happening at the infinity.
Spatial infinity.
And the most possible blow up for the torus would be at 0, but it's not happening, right?
Yeah, not happen. But as for CFR data, that will have blows up actually everywhere.
Okay.
The problem is on the circle is actually happen everywhere.
Okay.
Yeah. So that includes the infinity, you can think. Yeah.
Okay. So you have this A omega log.
Yeah, A log A.
Inequality. Do you expect you have like sharp double exponential behavior or?
No. For example, in this argument, this estimate is very weak. Oh, but in this case, in one case, you have to prove to achieve the double exponential growth. That's hard. I think there's a small scale formation, but I think for this kind of model, it's quite difficult. But in fact, from this estimate in the first case, you can indeed derive that this energy like the vortex, the solution can grow at most triple exponentially fast from this estimate in this case. But in the borderline case, we don't know. The estimate is very poor. So it's something like you can grow very, very fast, exponentially. Like 5, 6 exponential in for time period of time. Yeah, that's very bad and a power estimate, but still control the solution. Okay, thanks for your question.
Other questions? Let's thank the speaker again.